So welcome everyone to the Observing and Modeling Climate Variability in the Intra-Americas Seas and the Impacts on the Continental Americas and the Caribbean, our virtual workshop. This is Kristen Uhlenbrock from the CLLI Project Office. I'd like to go over just a few housekeeping items before we get started. First, if you have any technical difficulties during the webinar, the best way is just to contact ReadyTalk directly. You can do that via the number here on the screen, or you can do an online chat with them if you go to readytalk.com, and they have people standing by. We have 2 oral sessions today. The first one is from now until 2:30 p.m. Eastern Daylight Time, and then we'll break for 1 hour and host a virtual poster session, which we all hope and encourage you to attend. We'll return at the 3:30 p.m. Eastern Daylight Time for the second session and the second set of talks. We'll wrap up today's workshop at 5 p.m. And if you go to IASCLiP.org, you'll see the link for the workshop agenda and all the posters kind of there on the home page. You can check that out to kind of see everything we have going on today. So you'll look at the abstracts as well as any of the poster sessions. So like I mentioned, we really encourage you to attend the poster session during the hour break today in addition to stretching your legs. You can ask questions and post comments for all the authors to respond to. The poster presenters will be online and active during this hour, ready to engage with your questions. We will be recording this workshop and we'll make an archived version available online shortly after it is over. As many of you are aware, you are all currently on mute, and you're going to remain on mute during the presentations. Each presenter has about 15 minutes along with 5 minutes for Q&A. And then during the Q&A, there'll be 2 ways for you to ask questions. One way is to just type in questions in the chat feature that you see in the upper left-hand corner of the screen. We'll be monitoring these chat questions. And just so you know, only the presenters and the chairperson can see the questions, not the whole audience. But we will read those questions aloud to the presenters, queuing them up as they come in. The second option, and this is for those who have either connected via your phone or with your voice over IP, is that you can raise your hand. You can do this by clicking on the middle button on the screen. That's the raise hand button. During the Q&A, we're going to alternate back and forth between questions that come in from the chat window and those that raise their hand. And so when you raise your hand and we call your name, we'll take you off mute, and then you'll be able to ask your question aloud. Do please remember to keep your questions succinct and to the point, since we only have about 5 minutes for Q&A. After the 20 minutes are allotted for the speaker, we'll move on to the next speaker. And then if you have any questions that did not get asked, or maybe that just come up at the last minute, you can go ahead and type those in the chat box to us. We're going to collect all of them and pass them along to the speaker after the workshop, and they will answer those and we'll send those back around to everyone else. I'd now like to introduce Chunzai Wang from the University of Miami, and he will be moderating and chairing the very first session. Chunzai?
Can you hear me?
Yes, go ahead.
Okay. Hi, hello everyone. This is Chunzai Wang, and I'm an oceanographer from NOAA UML, and I will be chairing Session 3, Weather and Climate Extreme Event in American. There are 4 speakers in this session. Each speaker is given 15 minutes, and at the end of 30 minutes, there will be reminder bell for speaker. Then we have 5 minutes for question. Our first speaker is Gabe Wiki from GFDL. He will talking about a unified system for understanding, predicting, and projecting regional hurricane activity. Second speaker is me. The title of my talk is Impact of Atlantic Warm Pool on Atlantic Hurricane. Our third speaker, Yolanda Sarah from UW, and she will talking about diurnal to intra-seasonal variability and Central American drought. Our final speaker is Angel Niño from International Research Institute. He will talking about sub-seasonal to seasonal extreme rainfall in Caribbean Sea. Now I would like to welcome our first speaker, Gabe Wiki, to start our presentation. Gabe? Okay.
Thank you. It's great to be here. So I'm gonna narrow the focus of my discussion to the prediction seasonal timescales of regional hurricane activity, which is part of a larger effort to build sort of a unified system to understand, predict, and project regional climate and extremes. So this is sort of a narrow snapshot into a much broader effort, and you can see by the long list of authors that this is, at its essence, a very collaborative project. It involves, out of necessity, a large number of people working well together. So generally, we have a paired hypothesis and practical goal that we're pursuing. The hypothesis is that enhanced resolution in climate models and correcting errors in the large-scale climate will help us improve the simulation and prediction of regional climate and extremes. And that is very much connected with a practical goal sitting in NOAA, a mission agency, which is to build intraseasonal to multi-decadal prediction systems to provide better large-scale climate information and also enable us to predict regional climate and extremes. The context on the longer scale for what we're going to be talking about here is changes in hurricane counts in the Atlantic. Showing here is an annual count of the number of hurricanes hitting the U.S. on the top panel from 1878 to 2008. You can see substantial variability year to year, also some clustering on decadal timescales with a period in the 90s to the 2000s being relatively active, and the 60s and 70s being inactive. And you can find other clustering on multi-decadal timescales. And then you can look down on the basin-wide frequency. This is the total Atlantic frequency. It's the second panel. Again, you see some of the features you saw in the Atlantic manifest there, with certain years that were active in the U.S., being also active basin-wide. But there is actually somewhat a difference between what happens in hurricanes hitting the U.S. and what happens basin-wide, and that you can see by looking at the fraction of storms making landfall in the U.S. in the bottom panel, where as much of the variance on year-to-year timescales of U.S. landfalling hurricanes comes from basin-wide activity as well as from the fraction of basin-wide hurricanes making landfall. So if we're interested in trying to predict hurricane activity at a regional scale, in this case U.S. landfalling, we need to both understand basin-wide activity as well as the regionality or the susceptibility of any given storm making landfall. And so that's going to be, that second question is going to be a harder question to answer. Now, on the basin-wide activity, we've done a lot of work here at GFDL, as well have others in many other places, starting with Bill Gray's pioneering work, to try and predict the total number of storms or very aggregated indices of hurricane activity in the Atlantic. And one of the recent results that we've done is build a very simplified hybrid statistical-dynamical prediction system for seasonal timescales, where we build a statistical model to emulate a high-resolution atmospheric model using sea surface temperature as a predictor. And then we use initialized coupled model forecasts to predict the future values of the indices that are our predictors in our statistical model. And so we then apply that statistical model to the predicted sea surface temperatures and make a prediction of the full probability density function, or the PDF of hurricane activity for any given year in the Atlantic. And retrospectively, and also in real-time prediction mode, this system has done relatively well, initially giving us very long lead predictions. You can see here, initialized January, we got retrospective correlations exceeding 0.6. That's a 3-season forecast. So that's pretty exciting. Now, that's with a single model, as the model predicting the future values of SST. One of the recent advents in predictability science has been the North American Multi-Model Ensemble for Seasonal Prediction, or the NMME, which brings together a number of groups that try and collect seasonal predictions. And so my colleagues, Gabriele Villarini and Beda Luitel at the University of Iowa, have been building a sort of a Bayesian model average of this hybrid scheme using all the NMME models. And what we find is that across the two key predictors, which are Atlantic main development region sea surface temperatures, and then also tropical mean sea surface temperatures. The different NMME models show different levels of skill, both in correlation coefficient in the top and mean absolute error, with some of them showing slightly higher skill, some of them showing slightly lower skill. But we can then bring those together and sort of make correlations of the, so we can see how the system would have done predicting retrospectively from 1982 to 2013. The bottom panel shows the dots show the observed hurricane frequency in the Atlantic, and then the straight line with the shaded areas show the multi-model prediction for each given year, and you get a pretty good correlation. The interesting thing that we found there is that if we start excluding models, we do worse. So when you do the multi-model average, it's your best forecast, or the multi-model combination. And even if we exclude the worst model, a model that when you look at it, it seems to perform very poorly, suggesting that this multi-model average is in fact providing independent information. That's one of the things that we were hoping for when this multi-model average or the multi-model experiment was set up, but it's actually nice to see. So there's some evidence that we can go forward with some predictions of basin-wide activity. But basin-wide activity is something that's been predicted by a number of groups and is in real time, but it may not necessarily be the most valuable. Here is an example, I think, from recent history, where on the left we show here each one of these symbols, the red, yellow, green, blue, purple, and more other purple, show the number of Atlantic hurricanes predicted before the 2010 season by a number of different forecast systems. And this horizontal line shows the 1981 to 2012 average, and you see that all the systems predicted that 2010 was going to be basin-wide an active year. However, and observations came in at that value. So the observations got the message from the forecast, and it verified very well basin-wide. However, as you look in this right map over here, none of those hurricanes in the Atlantic made landfall in the U.S. as the Atlantic. Made landfall in the U.S. as a hurricane. Some of them did make landfall in Mexico and in Central America's hurricanes, and there were fatalities from some of them. But if you were interested in predicting storms in the U.S., that correct basin-wide prediction for 2010 would have not been very valuable. And so the question we want to ask is, can we predict in some reliable fashion the statistics of storms more regionally than basin-wide, more regionally than looking at the entire Atlantic, that after all is a very large and diverse area with different hazards and different countries involved. So in order to do that, we built a high-resolution experimental couple seasonal to decadal prediction system. We call it FLOR. Again, the goals of this were very much the goals that I laid out on the first slide. And what we did is, in order to be able to address regional climate and extremes, we increased the resolution in the atmospheric component from our old model CM2.1 over here on the left that is a 2-degree atmosphere. We increased the atmospheric resolution and land resolution to a 50-kilometer atmosphere, giving us about 20 more tiles per tile in this new model. But in order to remain efficient, we kept the ocean and sea ice components at a relatively coarse resolution of a 1-degree model. We've done a fair deal of analysis of this model in a number of ways, and it's shown itself to be useful for a number of things. But very germane to this talk is its ability to, as a coupled climate model running just with radiative forcing, reproduce the statistics of tropical cyclones. The left panels here on top to bottom show the simulated tropical cyclone genesis locations for observations on the top, and then the FLOR model in the middle, and the right panels show the same two but for tracks. And what you can see is that overall the model recovers a lot of the statistics. You get the main genesis in the subtropics, you get relatively little genesis in the Southeast Pacific and South Atlantic, and so it looks like a pretty decent model. Especially if you compare it to many of the other high-resolution models out there that have primarily been run with forced SSTs. However, if you're interested in regional hurricane activity, there's some deficiencies that pop out immediately. Here, if you look at the West Atlantic, there's a very big absence of storms. In the Central Pacific around Hawaii, there's an excess of storms. And we had a hypothesis. This model tends to have biases where it's very cold in the Atlantic, has high shear, very hostile towards tropical storms. We decided to create a flux-adjusted version where we create a climatological adjustment to the fluxes that artificially makes SSTs look better in a climatological sense, although it still allows the model to maintain variability. And that's what's shown in the bottom panels. And what you can see is that there's a marked improvement in the simulation of tropical storms by correcting the mean state errors. And so what that tells us, and we've looked at precipitation and other patterns, is that a lot of the biases in the ability of the model to simulate regional climate and extremes come from biases in large-scale sea surface temperature. And so the idea there is that if we can improve the large-scale biases in our model, we'll end up improving also the representation of regional climate and extremes. Now, getting to the question that I wanted to ask, which is, can we reliably predict statistics of storms more regionally than basin-wide? Here's a partial answer to that question. This is a 48-member average, and what it is a skill map. Shaded in colors are places with statistically significant rank correlation between predicted and observed storm density. So what we're asking there is, can the storm distinguish years with many storms within 10 degrees of a place from years with few storms within 10 degrees of a place over a season? So we're not looking basin-wide, not looking over the entire Atlantic, but we're looking over a region that's still very large, 10 degrees by 10 degrees. And shaded is places where there's significant correlation. And all the significant correlations are positive. Some of them over here, like over Guam, are incredibly large. And so this indicates is that there's at least the possibility to predict on regional scales tropical storm activity, even in some areas that are actually close to land. Here in the Gulf, there's some non-trivial, there's some significant skill. It's not very large. It's not like 0.9, but it's what it is. And this is a single model, and one wonders if a multi-model might actually end up doing better. So we also found that the prediction skill is improved by flux adjustment. So in here are two measures of forecast skill. I'll just focus on the one on the left, which is the percentage of tropical cyclone areas with significant rank correlation as a function of lead month. And what you see, the black line is the standard model, the blue line is the flux-adjusted model, and you see is that the skill of the two models becomes very, very distinct, especially at long lead times when the model's biases are able to reassert themselves, so that the flux-adjusted model essentially gives you an extra 2 months or 3 months or 4 months of skill in regional TC predictions, which is equivalent to quadrupling the number of ensembles for the first month. And then this was all retrospective forecast. This is one of our first real-time forecasts, the forecast for 2014. And the model correctly predicted that the West Atlantic was going to be active, but the East Atlantic was going to be climatological, and that there's going to be an increased activity in the Central Pacific. So this model then becomes a useful tool to do attribution studies. What caused the increased activity in each of these regions? Now, if we're thinking about, so going forward though, this model is useful for thinking about tropical storms at 50 kilometers. But the most impactful storms, the storms that cause most of the damage and human suffering, tend to be the strongest storms, the category 3, 4, 5s. And what you can see here is here shown the PDF, the distribution of intensity for black line, the observations of the different storms around the world, and the blue line is for the floor model, the 50-kilometer model. You can see that the floor model at 50 kilometers is unable to really distinguish storm intensities. The PDF is very narrow. Most of the storms are very similar to each other, and it has none of these major storms, about 50 meters a second, which are category 3, 4s, and 5s. We built a new model. It's called HIFLOR, high-resolution version of FLOR, which has a 25-kilometer atmosphere. And in that model, all of a sudden, we're able to resolve a much richer spectrum of intensity, including these major storms here, category 3, 4s, and 5s. This is from a 1990 control simulation, so a free-running coupled simulation. Not only are we able to distinguish the climatological PDF better, But we're able to, in an SST nudge, when we provide SSTs as a boundary condition, recover a lot of the observed history of number of Category 4s and 5s in the Atlantic. Shown here is the black, the number of Category 4 5s in the Atlantic, and the red is the number of Category 4 5s in the Atlantic from an ensemble of high-floor experiments nudged with observed SSTs. The blue line, that horizontal line, is of course from floor. There are none. So moving from 50 to 25 kilometer greatly improves our ability to represent these storms. And we've had some very encouraging results from experimental seasonal predictions where this SST force skill seems to emerge also in initialized predictions, and not only at the basin-wide scale, but also on some regional scales. So just in summary, a multi-model ensemble yields improved predictions of basin-wide Atlantic hurricane frequency, and I think what we see there is that the NMME models are really providing independent information. Even if you remove the quote-unquote worst model, we end up doing worse. So it's better to keep all the models in there. Increased atmospheric and land resolution is essential for enabling forecasts of regional climate, but also improves forecasts of large-scale climate. It also appears feasible to do predictions of a regional TC activity on seasonal timescales, but we need tens of ensemble members to really make them useful. And correcting large-scale errors improves the simulation and seasonal prediction of regional climate and extremes. So thank you.
Great, thank you. Chunzai, you're off mute. Any thoughts or questions before we go to the audience?
I would like to give the opportunity to the other people.
Okay, great. It looks like we have a question from Juliette Perdijon. Apologize if I messed up your last name. Juliette, you are off mute. If you have a question, feel free to ask. Hi, Juliette. Can you hear me? Great. So maybe you're on mute. We can't hear you very well. So go ahead and type in your question in the chat if you have one. I'm going to put you back on mute. Great. Do we have any other questions? Yes, we do, from Vasu. Vasu, go ahead.
Gabe. Hello, Gabe. It was a wonderful talk. This is Vasu Mishra from Florida State University. So this is very promising that you are able to focus in on region-specific hurricane counts. Do you consider the skill coming from initial conditions? Is it an initial value problem? Or do you see some kind of a large-scale forcing?
So that's a great question. By construction, this model, a lot of it, the skill, the way we initialize these model runs that I showed here, we did not initialize the atmospheric state with anything but an AMIP run. So it's all the skill that we're seeing here. This is essentially a lower bound on skill. It's coming from sea surface temperatures. Now, it's an initial value problem for the ocean and atmosphere coupled system, but if you're thinking about the atmosphere itself, it's a boundary value problem. So I think that we have some evidence that we can do better by also initializing the atmosphere and extracting even further information by getting things like the NAO and other things in much better alignment with observations.
Now, this skill, if I understand, comes from your flux-corrected model. And as you move forward to make projections, what are the plans? Do you plan to continue with this flux-corrected model for projections as well?
So I think there's reasons to be cautious about using a flux-adjusted model. And I wouldn't say flux-corrected because I don't think we're making the fluxes any better. We're just changing them. But there's reasons to be cautious because the flux adjustments now need not be the flux adjustments for the future. At the same time, I think what this should raise is a concern about the fact that we're running projections with biased models, and the biases are first order important in our ability to simulate the regional climate and extremes. So I think that we need to either really improve the biases in our models or come up with some very clever ways to artificially correct them. And so I don't know. We're in exploratory mode at this stage, so I'm not going to advocate for anything.
Great. Thanks, Vasu. We have one more question from Ernesto Munoz. Ernesto, go ahead.
Hello, can you hear me?
Yes, go ahead.
Hi, Gabriel. I have a few questions, but I'm going to just focus on one.
You're a little quiet. Just speak up a little bit. Thank you.
How about now? Is this better?
Better.
Okay. So my question is, how do you think that higher land resolution improves the forecast of the cyclogenesis?
That's a good question. I think it's relatively straightforward why higher atmospheric resolution would help. But I think that the higher land resolution in certain areas, especially in the East Pacific, where there's some indication that some vorticity sources coming off interactions between the atmosphere and topography may be important, could help improve the cyclogenesis climatology and also the forecast. We have some experiments underway where we're artificially degrading the orography in the model to see if that is a reason. But I think it'd be kind of neat if it matters. But even if it doesn't matter for cyclogenesis, higher resolution on land, it does matter for impacts over land. So we'll keep the higher resolution over land.
Okay, yeah, that was my next question. Maybe you were more interested in the impacts also, with respect to the higher land resolution. Okay, got it.
And yes, and even with tropical cyclones, you see that some of the biggest flooding events inland have happened when tropical cyclones interact with orography. So as it coming up the Appalachians, and so we'd like to be able to represent some aspects of that.
Nice. Okay, thank you.
Thanks, Ernesto. And thank you, Gabe. We'll go ahead and wrap up your presentation here, and we'll go on to the next presenter, which is Chunzai. Chunzai, you can go ahead and take controls.
Okay. Okay. I was talking about the Atlantic whirlpool impact on the Atlantic hurricane. The co-author of this paper, this talk is Sung-Ki Lee, and David Enfield, and Hailong Liu, and Bob Atlas. In 2001, we published our first paper about West Hemisphere whirlpool. We defined whirlpool by SST larger than 28.5 degrees C. And basically, West Hemisphere whirlpool has two parts. One part is in East Pacific. One part is in Atlantic part. The East Pacific whirlpool started to develop in March, and then peak in the May. And after May, East Pacific whirlpool started decay. At the same time, Atlantic whirlpool starting to develop in June, and peak in September. In today's talk, I will focus on Atlantic side whirlpool. We call Atlantic whirlpool. So how I can go to next? Where? Oh, okay, here. And this slide shows Atlantic whirlpool index, and the index is defined by whirlpool area, normally divided by climatological whirlpool area. So unit is a percentage. The top panel shows total whirlpool index. The solid line is linear trend. The second panel shows the trend whirlpool index, which means we remove linear trend. And the third panel shows multi-decadal variability for whirlpool. And the last panel shows interannual variability of whirlpool. So basically, Atlantic whirlpool shows seasonal, interannual, multi-decadal, and linear warming trend variation. And this slide shows the relationship between Atlantic whirlpool and tropical storm. We use past 54-year observational data. We choose 18-year large whirlpool, and we choose 18-year for small whirlpool, And the top panel show the hurricane storm track for the small warm pool case, and lower panel show for large warm pool case. So we first take a look at the 18-year small warm pool case. So for the 18-year small warm pool, we only have 3 busy hurricane season. Total we have 23 storms. However, for 18 large warm pool year, we have 11 busy hurricane season, and total we have 82 storms. So this composite tell us warm pool large warm pool will increase the number of the hurricane. So question is why? So next slide will show. Next slide show why. So here what we did here is we use the observation data, and then we calculate the regression of the water wind shear between 800 millibar and 200 millibar onto the warm pool index. And this box is so-called Atlantic Hurricane Main Developer region. So people call MDR region. So over this region, we have strong negative value. What does it mean? This means when warm pool larger, water wind shear over MDR region is decreased. When warm pool is small, and the water wind shear over this area is increased. So, and the increase water wind shear is unfavorable for hurricane, and the decrease of the water wind shear is favorable for hurricane. This is why large warm pool will increase the number of total hurricane. This observation, we also use the atmosphere GCM model to study the Atlantic warm pool. So basically, we perform 3 group atmosphere ensemble run. So first group we call control run. What control run mean? Control run mean the global model is forced by climatological SST. And then we perform large warm pool ensemble run. And for this ensemble run, in Atlantic warm pool area, model is forced by SST composite for large warm pool year. And outside the warm pool area, we still use the climatological SST force the model. Similar situation for small warm pool ensemble run. Then we take a look at the model result. And this shows the atmosphere GCM model result. What we show is the water wind shear between 200 millibar and 850 millibar. Left panel shows the control run for water wind shear. So basically, this is consistent with the observation water wind shear. The right panel shows the difference between large warm pool run and small warm pool run. We see over the Atlantic Hurricane Main MDR region, that the blue color over there, which means water wind shear is reduced. So large warm pool will reduce water wind shear over Atlantic Hurricane Main Developer region, which is consistent with the observation I just showed you. Next, we take a look at the why. So why is large warm pool reduce water wind shear over MDR region? And here is also the difference between the large warm pool and small warm pool run. What we show here is the gel protection height and wind. Top panel shows 200 millibar. Low panel shows 850 millibar. We first take a look at the upper level. Upper level model response show anomalous anticyclone over here. So over the MDR region, we have a strong easterly wind over here. And this strong easterly wind anomaly will reduce the mean westerly wind over upper level. Then we take a look at the low atmosphere. Look, in low atmosphere response is anomalous cyclone. Anomalous cyclone over here. And over MDR region, we have a strong westerly wind anomaly. And this westerly wind anomaly also reduces the easterly trade wind in low troposphere. So the net result is large warm pool will reduce water wind shear over the hurricane MDR region. This is a mechanism for the warm pool induced water wind shear change. Next, what we show is also model result. What we show is a CAPE. CAPE basically represents atmosphere instability. So left panel again is the control one. So over one pool region we have a large CAPE is a large value, which is atmosphere is a favorable convection. For the difference between the large warm pool, small warm case, we have positive value, which means large warm pool will increase the CAPE value, which is a favor for atmospheric convection, and then we have more hurricane. Next, we move to another topic, the hurricane track. And before this slide, what I show is hurricane number. Next, we show the hurricane track. We first use observation, and this panel, what I show here is the regression of the hurricane track data onto the warm pool index. You see the contour value. By the way, the shading represents 95 significant, and the contour is positive everywhere, which is consistent with the large warm pool where increase hurricane activity in Atlantic Ocean. We also, you see, we have two maximum. One is over open ocean area, another over Gulf of Mexico. And in this max value over Gulf of Mexico is due to the tropical storm formed locally. To prove that, we remove the TC formed locally, then repeated our calculation. Then this is what we got. So this means maximum over there is due to TC formed locally. And another feature is this. You see that the regression pattern is from south to north. So this kind of pattern, if a hurricane form here, hurricane will continue move northward without make a landfall to U.S. So this figure tell us that warm pool is unfavorable for hurricane make landfall to U.S. So why? So why the warm pool change hurricane track? There are two ways. One way is Atlantic warm pool change hurricane genesis location, then change the hurricane track. Second is warm pool will change atmosphere circulation, and then change hurricane track. We first take a look at this, the hurricane TC genesis location with or Atlantic warm pool. So here is the result. What we did, we used the last 40-year observation data here. We chose 10-year large warm pool and 10-year small warm pool. And the shading here shows SST contour, the large warm pool, small warm pool. The dot over there is a TC genesis location. We'll first take a look at total number of TC for 10-year large warm pool and then 10-year small warm pool. Obviously, large warm pool favor increase the total TC number, just as I showed you earlier. However, what this figure I want to point out is for large warm pool, TC genesis location move eastward. So eastward shift of the TC genesis location decrease the possibility for hurricane make landfall to U.S. This first. The second, we take a look at the TC steering flow, hurricane steering flow. Again, this observation, we chose 10 large warm pool year and 10 small warm pool year. Then make a composite. Left panel shows the 10-year large warm pool TC steering flow. We see over the east coast of U.S. and Gulf of Mexico, the wind anomaly is northeastward. And this kind of TC steering flow is not favorable for hurricane making landfall to U.S. The opposite is true for small warm pool. You see that we have the wind reverse direction over here, follow this way. So this observation suggesting large warm pool induce TC steering flow, which is unfavorable for hurricane make landfall to U.S. This is the observation. We also use the model to take a look. Again here we show is the difference between the large warm pool and small warm pool, and this panel shows TC steering flow, and it's similar to the observation. And left two panels shows sea level pressure, and the top panel shows large warm pool case, and the small low panel shows small warm pool ensemble run. We use the contour 1021 millibar as a reference into the subtropical hair. You see, for the large warm pool case, subtropical hair move northeastward. And however, for the small warm pool model run, the subtropical hair crosses the whole Atlantic Ocean, reach east coast of U.S. So if a hurricane form in here, and this kind of subtropical hair pattern will make a hurricane favor to make a landfall move westward, make a landfall to the southeast U.S. However, for the large warm pool case, if a hurricane form in the MDR region, the hurricane will move westward and then they curve northeastward, go to without making landfall to southeast U.S. And this is our major conclusion here. So here I give a summary here. The summary that basically warm pool impact a hurricane that two effect. One is the total number. So a large warm pool will increase the total number of Atlantic hurricane. And the mechanism is due to two. First one is large warm pool will reduce atmosphere vertical wind shear, and which is favorable for hurricane. And second, large warm pool also increase atmosphere instability, and this kind of change will favor atmosphere convection, so the total number of the hurricane will increase. Second one is about hurricane track, and what we got here is a large warm pool is unfavorable for hurricane to make landfall in southeast U.S. And this conclusion is consistent with last 10 years. You know, during past 10 years, no hurricane make landfall in southeast U.S. That one exception is 2012, the Hurricane Sandy, and move northward, make landfall in New York and New Jersey, made a large damage over there. This also consistent with our conclusion. Our conclusion is large warm pool, ocean is warm. The hurricane, because the warm ocean will change atmosphere circulation. Atmosphere circulation will steer the hurricane move northward or northeastward without making landfall to southeast U.S. The mechanism for the hurricane track is also through two mechanisms. First one is large warm pool will induce atmosphere steering flow, which is unfavorable for hurricane to make a landfall in south U.S. The second mechanism, large warm pool will shift the TC genesis location, which also decrease the possibility for hurricane to make a landfall to southeast U.S. Basically, I stop here, and if you have any question, we can discuss. Thank you.
Great. Thank you, Chunzai, for that great presentation. At this time, we'll take any questions. If you have some, please type them in the chat or raise your hand. Chunzai, looks like we have a question from Germain. He asks, what is the relation between the size of the Atlantic warm pool and El Niño, La Niña, having in mind the connection with hurricanes?
Oh, yeah, this is a good question. Is that we know the El Niño will decrease total number of the Atlantic hurricanes. This we know 20 years, 30 years ago. And about the hurricane track, we also, in our paper, we also study, but I did not show in today because only 15 minutes. So it's basically La Nina is favorable for hurricane make landfall to the southeast U.S. and El Nino is unfavorable for hurricane make landfall to south U.S. I have a figure here. I want to show. Let me see where I go. I want to show this. Anyway, in my backup slide, it shows basically the La Nina is unfavorable for hurricane to make landfall. So the question is, if this year is a La Nina year, and the Atlantic warm pool is warm, so which will be one is favorable for hurricane making landfall, another one is unfavorable. So net result depends on competition. So which the ENSO impact is larger, then hurricane will make landfall. However, if it's local Atlantic warm pool impact is larger, dominant, then is still unfavorable for hurricane to make landfall. The conclusion here is depend on competition between the Pacific Ocean and the Atlantic Ocean. So yes, the ENSO also impact the hurricane. Yeah.
Thank you. And we have another question, and then we'll move on to Yolande. The other question is from Eric Alcero. He wants to know, is it expected more impacts on the Pacific slope for Central America during a small Atlantic warm pool years associated to the systems traveling in the Caribbean basin?
The question, what the question is Central Pacific?
Yeah. Or he asked the impacts on the Pacific slope for Central America during a small AWP year.
I mean,
associate. Eric, let me see if your audio is connected.
Let me see. Is the question over there?
Eric, does your audio work?
Impact on the Pacific slope for Central America during small warm pool year associated with the system travel.
Yeah, did you understand that?
In Pacific slope, what slope? You mean summer class?
No, I mean there are two kind of impacts on the Pacific or on Central America because tropical systems traveling on the Caribbean. One is the landing, that is the direct effect, and the other one is the indirect effect because of the circulation induced across the isthmus because of the low pressure traveling in the Caribbean basin. Do you get it, or am I interpreting right your figures, or I'm wrong?
Yeah, it's actually as I said earlier, the East Pacific, Central Pacific's influence on hurricane is also slow the water wind shear. For example, Pacific SST change or change the water wind shear or Atlantic hurricane region, and this so I did not mention and show the Central Pacific and Pacific influence because this is not new result. So I only show the Atlantic warm pool impact on the.
No. Central America has two slopes, a Caribbean slope and a Pacific slope, okay, because of the mountain change that cross the isthmus. So it is when you have a low pressure on the Caribbean, you have an induced circulation from the Pacific to the Caribbean because of the low pressure crossing the Caribbean Sea. So if I get right your figures during small warm pools, there are more low pressures near the Caribbean basin. So it means also if I got the figure right, it will mean also more impacts because of the heavy rains on the Pacific slope of Central America. But that's my interpretation. Maybe I'm wrong.
This is possible. However, what I show here, I show the model result here, right? I show model result. In our Pacific Ocean, no change over there. Only change is in model false is in Atlantic warm pool region, which means from observation part of view is totally due to the Atlantic warm pool change. It has nothing to do with the Pacific Ocean, based on our model result. But from observation part, yes, you are right. You cannot remove the Pacific influence, but our model result show is only due to the local Atlantic warm pool influence. Thank you.
Great. Thanks, If we don't mind, we'll go on to Yolande, and we'll take any questions maybe at the end, or we'll type those in chat, and we'll let Chunzai respond back so we can keep on track.
Okay.
Okay. Thanks, everyone. Yolande, you should be up. Can I test your audio? I think I heard you.
Yep. Can you hear me all right?
I can hear you great. Go ahead and take over controls, and we'll put everyone else on mute.
Okay. I really should have probably done diurnal to interannual here on this title, but I'll just jump right in. We'll go to the outline. This is it's not changing.
Hover your mouse right above the slides, and you should see the arrows to show the next slide in the middle.
Yeah.
And then that's also where the there you go.
There we
and
go.
then the green pointer if you want the green pointers to the left as well.
It wasn't
Great.
responding. Sorry.
Sorry, a little slow.
All right. So this is just a summary. This is a sort of new material, so I'm not really going to draw conclusions here. I'm going to bring up some ideas about some scale interactions and associated with the current drought and perhaps previous droughts. So I'll show you some slides of the current drought to give you a sense of what it looks like, and some discussion of the really it should be global tropical SST forcing that's been associated with droughts in the past in this region, and then bring up some of the local processes that may be modulated by these larger scales and how they so discuss some of how they're modulated and then how they relate to one another, and how we can try to connect the chain of scale interactions to get to the local impacts over Central America in the rainfall. And then I'm just going to briefly then look at some of the current observing systems in the region to see if they're really sufficient to get after some of these questions. Okay, so this slide shows the rainfall anomalies over the past 5 years, and I've chosen these years because at the end of the talk you'll see the observational network I have down there really only covers back to 2011. But anyway, you can see that the characteristics of this drought, although over Central America it's been persistent for 5 years, over the region as a whole is fairly different depending on the year. So quite a bit of interannual variability in the precipitation anomalies in the region, with 2014 and 15 looking perhaps the most similar, but then these other years looking quite a bit different from each other and from these years. So this is important to keep in mind as we go through some of the other slides. Okay, so IRI has a nice site that shows you the drought probability associated with ENSO. So here they do terciles of rainfall anomalies. So I've chosen the dry tercile. You can look at the wet tercile or the neutral. So here red then these numbers are probability. So a 1 would be a high probability of a dry season, and we're looking at the summer, June, July, August season, and I'm looking at El Niño conditions. So these red numbers then mean high probability of dry for El Niño, and in this box here to the right, or the plot to the right, we show low probability of dry during La Niña. So it just shows that the ENSO has a fairly strong signal as far as warm years are related to drought over the region. So if we then go to the next slide and look at what ENSO has been doing over the years. It's not responding, I'm sorry. There we go. So here's 2011 through the current period is in this latter half of the time series. And we see that, for instance, 2011 was a La Nina year, pretty strong La Nina year, with some sort of a break here. But then we have some ENSO years as well, particularly 2015 with a very weak one in, end of 2012, I guess. So, and then some weak La Nina conditions in 2013 and 14 is a transition year. So this may explain some of the variability in the rainfall patterns throughout the region, but the previous slide has shown that ENSO itself, it's not responding, sorry, is associated with the drought over Central America, but ENSO was not persistent throughout the 5 years. So other factors are contributing to the Central American drought. But nevertheless, that seems to be an issue. So to look more now at the local conditions and how they might be modulated by ENSO, we're going to start with the Caribbean low-level jet. This is kind of a review paper from Amador, 2008, where he has looked at, this is a 2000 to 2007 climatology of wind stress from the QuickScat satellite of the winds here in the Caribbean. We see here the red notes the maximum, the high values of wind stress, and then the arrows are the direction and strength. And this is for July, and the bottom plot is for February. These are the two maxima in the low-level jet across the seasonal cycle. And what we see here is that the winds are, the trade winds get, there's a maximum in the trade winds here with the low-level jet. They pass across the topography of Central America into the East Pacific. Here we have a monsoonal flow in July that opposes the easterly flow in this month, but in February we see the jets, the topographic jets coming straight through the land here and into the East Pacific. And if we look at then the El Niño impacts on the jet, what we find is for on the 925 hectopascal winds, we see a stronger jet. So these are stronger easterly flow during El Niño or warm phase of ENSO. And here are the precipitation anomalies consistent with what we looked at earlier, that there's negative precipitation anomalies over Central America. The point that Amador makes here in this paper is that a stronger jet also results in local divergence over the landmass, and so that is the local forcing that would reduce precipitation over the land here in Central America. So this is one way of how the ENSO would act to reduce rainfall in a local sense, local mechanisms over the region. Okay. So if we just look at, these are reproduced from the previous slide, the rainfall anomalies for these two different years, 2013 being somewhat of a neutral year, as neutral as I can get, but somewhat La Niña-like. And then 2015 being the strongest warm phase El Niño year. And what we see is that if we just look at NCEP reanalyses, these are actually the only ones available for the July 2015. Other ones hadn't been produced yet, but we see that the low-level wind, this is the 925 hectopascal zonal wind difference from 2015, July 2015 to July 2013. And we see, as the climatology shows, a stronger easterly flow over the eastern Pacific. So even though the jet is focused here, ENSO affects mainly the easterly flow on the Pacific side during ENSO. Okay. So change. All right, so some work that I did in 2010 also looks at how easterly wave tracks, which are another important climatic feature of the region, are impacted by the low-level jet. And so what we see here, the shading shows TD filtered OLR, so OLR filtered for the easterly wave convection, convection coupled to these waves. And then the contours are tracks density of vorticity, 850 to 600 millibar vorticity centers, low vorticity centers. So this is a tracking mechanism to attempt to track easterly waves across the basin. And so we see that they nicely match each other, showing that these two independent measures of easterly wave activity are consistent with one another over the region, and we see where the tracks tend to go, and that there's a maximum in the track density here in the East Pacific, in the just kind of north of the ITCZ, which would be somewhat more south of this area here as they propagate out into the Pacific. The ITCZ is just below them. And so this slide here simply shows an index, a low-level jet index that we created. It's positive means stronger easterly flow, so we see that maximum in July in the summer, and in the ERA interim, the maximum is in January, whereas the QuickScat puts it in February. Nevertheless, and then the 2 minima in the spring and fall. And if you blow up what's going on in, for instance, July, you can see that the jet also has a lot of synoptic variability. Here's a 10-day variability here, and then more like a 4-day variability on top of that. So the point is the jet varies across many scales, and as we've seen, it's also impacted by the ENSO, so even on interannual scales. So what we found is that during strong low-level jet periods, versus weak low-level jet periods, the difference in track density shown here of easterly waves. Easterly waves are more longitudinally oriented. The tracks are more longitudinal, and so they're shifted away from the coast, and there's actually more of them, so their number density increases. But probably more importantly, to the point I want to make here, is that they're shifted off away from the Pacific coast of Central America, rather than during the weaker phase where they tend to track closer to the coast. And so given that these are coupled to convection, as shown here, this could be a mechanism for reducing the rainfall on the west coast of Central America and across Panama in general, as you pull these waves away from the Central American landmass. And so not only would the low-level jet create diversions over the land, but you're also pulling these synoptic features away from the coastline, and again, perhaps feeding back to the whole drought, the situation of the drought in the region. So, and I think that these types of scale interactions need to be better understood. Okay, so there's I just threw this slide in. There are other mechanisms for making the tracks more longitudinal. This is a figure of the track density for easterly wave track density for the east minus west phase of the MJO. So another more 30 to 60 or 90-day variability in the region, and you can also pull the tracks away from the coast for these different phases of the MJO. Again, pulling convection, synoptic convection that might develop associated with these waves away from the landmass. This study shows that during ENSO, again we're back to ENSO, warm minus cold phase actually is consistent with what I was just showing you, pulls both this ECHM model and the ERA 40 reanalyses indicate that the waves get pulled out and are more longitudinal. This is a track density calculation identical to the one that is shown here and the one we used in our 2010 paper. So it's showing that the vorticity tracks are going more longitudinally. And then in the future period, I've been looking at even the CMIP5 model, and this was shown with CMIP3 as well, that the tracks become more longitudinal. So there's many mechanisms on many timescales that can impact at least the synoptic waves that pass over the region and generally produce weather over Central America. And so we care if they get pulled out away from the landmass. Okay, so even going down to smaller scales, here this is some work from Zender et al. 1999. It's an equatorial beta plane model that he used. I just want to show these results. So the heavy contours are the land in the model, and it's supposed to imitate or mimic the Central American mountains. You have easterly waves, or these Rossby waves, coming up, impinging on the mountains from the west, or from the east, excuse me. There's a background easterly flow, and then this vorticity maximum here, minimum I should say, is the ITCZ in the model. And what they find is that they get intensification as these waves impinge on the topography, and you get intensification of these Rossby wave centers on the coastal, on the leeward side, and they tend to go along the coast as they come out on this side. So, and when you remove the ITCZ from the model, it reduces the intensification of these Rossby wave centers. So the point being that the ITCZ, the topography, and these impinging easterly waves are all interacting to produce what we see as the synoptic conditions along the coast of Central America. So again, a lot of scale interactions that should be investigated more, and understanding how they're modulated by these low frequency factors in the region that might impact drought, for instance. This is also showing the diurnal cycle in the region. Here we see amplitude and phase. The amplitude over the land, of course, is larger than over the ocean, but you'll notice I show the global picture here from this Yang and Slingo paper based on satellite brightness temperatures for the June, July, August season, and you see that the amplitude, even out into the East Pacific in this region, is quite a bit larger than most of the open ocean regions in the world. So this is a very interesting basin to study for looking at the diurnal cycle and its propagation perhaps out. And we think it's propagation here. We see, because of this phase part here, where we see that the reds are the afternoon, and then as you go blue, you're into the early morning. So it appears that, of course, you get the afternoon convection over the land, and then it appears to propagate out. So the maximum over the ocean is in the early morning. And so, again, interesting to study on the local sense what is happening there and how it might interact with the waves in the region. And so here is a movie, I think. I'm not sure.
Yeah, I'm going to run that for you.
All right, thank you.
And Yolanda, just so you know, you're also at 16 minutes, so if we can wrap up here.
Okay, I will wrap it up right here. This movie just shows the development. This is just for a recent period in August in 2015. And just watch the movie. You can see the development, particularly over Panama here for this particular period, within this envelope of this easterly wave in the water vapor imagery. Okay, so I can escape the movie now. Do I just hit this slide? Okay, yeah. All right, so can we, I just want to go over some of the, just quickly look at some of the observational options we have in the region to look at these types of problems and even to constrain our reanalyses. I'm going to, oops, for some reason my text isn't showing up. The green is the most recent, so through 2015. The blue is, I believe, through 2010, and then the red is before 2000. So these are the radiosonde observations available, and you can see in Central America there aren't very many, and there aren't really any recent ones. Here we're looking at surface rainfall. Up through 2000 there seem to be a lot of reporting stations, but then most recently the blues and cyans we have very few. Okay, so and then here is we'll hear about CocoNet in the next session. John Braun will give a talk on CocoNet as a observational network. I'm just showing the sites that are in the Central American region. These are GPS data, GPS sites that provide precipitable water, so total column water. And I'm going to jump to some of the, just quickly what we can do. Here's the topography, and these are the sites, the warm sites being on the East Pacific side and the blue sites being on the, the warm colors being on the Caribbean side and the blues on the East Pacific side. And we can see, for instance, I'm just going to jump to this east-west transect that I chose that kind of that looks at these sites in particular. And you can see that there's this change in the phase of the diurnal cycle and the precipitable water, similar to what we saw in Yang and Slingo's rainfall imagery and or brightness temperature imagery, so that the Pacific side has a later peak in the diurnal cycle, and it's also wetter. So these are interesting things. We can use these data to investigate some of these issues with the phasing of the diurnal cycle and perhaps the development of organized convection out over the Pacific and its interaction with easterly waves as seen in that, that satellite imagery. This is the midsummer drought, so this is sort of a seasonal picture from these same data. And again, we can see the drier versus wetter regions and also the greater versus smaller midsummer drought regions, and try to understand even, this is a feature I didn't get a chance to talk about much, but these data are good for this, but I would argue that we are still needing more data in the region to investigate these questions. These were some reanalyses, the different representation of the low-level winds in the region from different reanalyses, our reanalysis 1 and 2, interim and MIRA. and I'm sorry, I'm rushing here. I thought I'd get through this. And this is precipitable water. Again, different representations and different models, making investigation of these questions difficult. So I will stop there. These are my summary slides.
Great. Thanks, Yolande. I'll leave these up for a second as we get Angel queued up. If anyone has any questions, go ahead and queue those up in the chat. We'll put those in a document, and we'll let Yolande answer those, and we'll make sure we send them around. We do want to keep on time, but that was a really great presentation. Thank you, Yolande. Angel, we have you off mute. Can we test your audio?
Yeah, 1, 2, 3, testing.
Wonderful. I can hear you just fine. Why don't we go ahead and get started with your presentation?
Okay, let's do it. Okay, let me see. So I can do this, isn't it? Okay, there you go.
Great, thank you.
So should I start?
Go ahead.
Okay. Oh, hello, everyone. I don't know if I think I need a presentation. I need to introduce myself. So my name is Angel Niño, and I'm a PhD student working with Lisa Goddard and Andrew Robertson and other people at IRI. And I'm going to be talking to you very briefly about some work in progress about how to identify subseasonal to seasonal extreme rainfall scenarios for the Caribbean Basin. It's a new methodology that we have been testing also in Southeastern South America. And well, just like as a motivation, most probably you all know that the National Weather Services in Central America, the Caribbean, and also in Northern South America are on a monthly basis providing seasonal forecasts for precipitation, temperature, etc. And also like very recently even extreme rainfall, frequency of extreme rainfall. But we are still providing seasonal amounts or on account of seasonal account of number of days exceeding a certain threshold for rainfall, for example, the 95th percentile. And decision makers are really interested in those kinds of products, but also it will be very useful and helpful to have also the distribution not only in time, but also in space of those metrics, of those variables. So what we are testing here is a methodology that could help a bit in that direction. So one way to approach the problem is to consider the daily atmospheric circulation patterns, something we're going to call here weather types. And we're going to be, I think that tomorrow there is a poster by Nicolas Vigo that is going to be also like presenting some of these results over there. So the idea here is like we want to try to understand what are the physical mechanisms and even like try to identify potential predictors for extreme rainfall for the region using these daily atmospheric circulation patterns. And something that we would like to do, in terms of this presentation in particular, is we want to take a look at, we want to try to identify potential predictors. So a question that one may ask is if these weather types tend to occur more frequently when we have certain sea surface temperature patterns. So that is something I'm going to be showing very briefly, and there is a lot of physics. I don't know if I will have time to talk to you about that, but maybe like in the question session or even like with Nicolas, because there are a few interesting things in terms of predictability. For example, we could also like talk a bit about how good dynamical models are actually representing these weather types. But even maybe the most important thing for me right now, I'm really interested in trying to show you how we actually we may be able to build this subseasonal to seasonal scenario so we can actually give information at subseasonal scale. If we can actually do that, if we can try to forecast these sequences of weather types, how can we build a model like that, and what will be the predictive skill associated with that model? So, well, let me just introduce you guys on this slide, like a bit of the approach, a bit of what we have been working with. So on the, let me show you this. Yes. So what we have here is K-mean solution with 8 weather types. Let's say, for the sake of the time, let's just say that is just like a cluster analysis using velocity potential at 850 millibars. We use that variable to be able to identify our weather types. Those are daily circulation patterns. And on top of that, I have the statistically significant moisture fluxes. So with a composite analysis, what you can do is like to identify what is the rainfall distribution associated with each one of those weather types. And then you can start playing and say, well, maybe if I have this weather type, number 1 or number 6, very frequently in a particular season or in a particular month or in a particular week, then maybe if I can forecast that, I will be able to say, well, that this is the frequency of extreme events that I'm going to have, and you can actually like provide information that is useful for decision making. We can talk about that a bit later. But in general, let's say that once I have these 8 weather types, which could be understood like a physically available state for the system, then I can try to use them to explain the observation in terms of mean rainfall or extreme rainfall or temperature or combination of those. And then one of these questions, as I mentioned before, is if for a particular season I have like a high occurrence of weather type number 1, could I relate that to a particular SST pattern that happened the previous month? And what we found in our research is that actually there are specific SST patterns that tend to happen for November, but also for September and for October. That could be, are good. Those are like good potential predictors for the predictant, which is the frequency of occurrence of these circulation patterns. We also did this for other variables. This is what you're seeing. There is obviously SST for that domain. So we found like something, not only El Niño, like the Atlantic has also something to do, but you can also do something like that, the same kind of analysis for MJO and NAO and other variables. And I'm going to skip that one because I want to focus on this. So this is sorry about that. This is just a bit of this art. I don't know if you know about Paul Klee or Clay. So he was really excited about this exploration of color sequences. And what we want to do here is actually to explore weather type sequences. So what we did in a recent paper is that we represented the weather types for let's say like for each season. Like this is December 1st, and this one is February 28th. So you have like the intraseasonal variation day after day of each one of these weather types for a set of 30 seasons. We are talking here about December, January, and February. We also did this work for June, July, August. I'm just going to focus here for the sake of simplicity and time for DJF. But the idea here, when you see something like that, you say, well, there is nothing here. This is just noise. And something interesting that we already know is that weather types are associated with particular rainfall patterns or extreme rainfall patterns, but also sequences. Like if I have one of these guys that is related, for example, to with advection, moisture advection towards, I don't know, for example, Jamaica, and I have persistence. That weather type is persistent. Like for example, see these guys here and here. So then maybe I will be able to describe. I will be able to explain the physical mechanisms associated with extreme precipitation. So this is the idea that we want to explore. What can we say in terms of sequences? So if you consider the Klee diagram, and then you work with an additional clustering method, let's call it like K meteorites. Let's say that it's just a categorical classification algorithm. You can try to find patterns and say, oh yeah, well, I'm not going to be able to describe exactly, what is like the state or the cluster that is, the sequence, the seasonal sequence for a particular year, but I can, in this case, identify 5 categorical clusters, 5 seasonal, subseasonal to seasonal states that describe this whole sequence for all those 30 seasons. And you can see, remember this guy, like a lot of persistence here. And for example, also, I don't know what I did there. Okay, now I'm back. So if you pay attention, you have 1985 with this kind of distribution, like blues, some reds, and then a lot of these guys together. You can also see kind of the same behavior for 2001. And our cluster analysis actually captures that and the state number 4. You have 1985 and 2001 and some others. So this is, well, obviously, the classification is not perfect, but it's robust. It's a good way to classify all those things that look like noise in the previous slide when we were just talking about the CLLI diagram. So the key idea that we want to explore here is once I have these subseasonal to seasonal states, what can I say in terms of mean rainfall, or in particular here in terms of extreme rainfall, or frequency of extreme rainfall? And what we find is you now do a composite analysis for each one of those categorical cluster or states. You find these kind of distributions, intra-seasonal distributions for extreme rainfall. What you are seeing here is the frequency of days exceeding the 95th percentile for each one of the 5 states that I mentioned to you before. And the method automatically discriminates between not only like in terms of the distribution, but also in terms of the expected frequency of days for each one of those states. So these are things that we're going to call the scenarios, the extreme rainfall scenarios, and are related to these guys that are the subseasonal to seasonal states. So what we want to do actually is to forecast the states, the categorical clusters. And then once we have that forecast and say the probability that we have state number 3 is, 80%, we will be able to provide what is the expected behavior for that particular state. And that is what we're going to call the extreme rainfall scenario. So just to see if that is clear, a typical forecast will be something like you have, from a dynamical model, you have the sequences or the frequency of occurrence of each of these weather types. Or you can also use, from a model, the SST field, or use November's observation of the SST field. We have tried like several of these predictors. For the sake of simplicity, let's say that I'm going to consider the frequency of occurrence, the predicted frequency of occurrence for these weather types, okay? And those are my predictors, and I want to build a multinomial logistic model to forecast the probability of each one of these states. So again, let's say that I find that for 1998, I'm going to have like a high probability of this guy, state number 4. So once I have that, I say, well, I want is the 95th percentile, do my composite analysis and find, well, sorry, in this case, I'm just showing the scenario number 1. And I say, well, this scenario will expect the occurrence of more extremes during the 10 first days of the whole season. And associated with that period, or, 2 months, or the middle month, or just compute the statistically significant spatial distribution for your frequency, and you will be able to have not only the subseasonal information in terms of the distribution of extreme events, but also you will be able to have an idea of what is the spatial distribution. So I'm about to finish. I don't know how many minutes I still have, but this is an example of this particular model. So one of the questions that we had at the very beginning with our research question was, what is the skill of the model? So once you train this model, this is a multinomial logistic model, you can say, well, for each one of the years, these are the probabilities for each one of the the scenarios or states. Now you know that those are related. And this is what actually happened. And you can compute the typical skill metrics, and you find like really good numbers. Remember, for example, the heat score needs to be compared to the climatological expected value, and that is around 20%. So this is actually good. The Kendall Tower is also really good. Typical values for this, if you want to forecast for the Caribbean, rainfall or extreme rainfall are around 0.1 or 0.2 in the best cases, and this is a very high Kendall's Tower value. So the model is not perfect, but it's behaving well. So, for example, it's not really good for if you will want to forecast accurately states or scenarios classified here as free. As you can see, this is the forecast and this is observed. So not doing a good job there. But it's really, really good with, for example, state number 4. And that state number 4, if you remember, is the one that was associated with those examples that I mentioned before, 1985 and 2001. So in this case, it actually has a perfect discrimination. It's not confused by other states. This is also a good one. When it forecasts one, most of the time is right, but it has some confusions too. So this is still work in progress. The model is behaving well. We can have like it's not a forecast for extreme scenario, subseasonal to seasonal extreme values. But we have some scenarios. What we are doing is trying to provide additional information to the decision makers or the community in general, trying to say this is what you should expect, given that we have these probabilities for what we are actually forecasting, which is the subseasonal to seasonal states. So I hope that I'm okay in terms of time. This is my summary. Maybe you remember that I asked a few questions at the very beginning, and I'm just answering a few of them here right now. Basically, I want to focus on on these two. This is what I have been presenting, what I've been talking to you about is basically about this predictability study using this new methodology or new model, if you want, a categorical model. And well, the answer is actually yes, we can forecast these subseasonal to seasonal states using these multinomial logistic regression models. And actually, the predictive skill is fairly good compared to climatological values. And actually, when you compare that to a typical predictability experiment that you have in the region. The model is not perfect at all. It's good. It's really good for to forecast state 4, but is, for example, really bad for state 3, as I mentioned before. And it has you saw that in the contingency table or the confusion matrix. You can see, you can evaluate, and you can even say, well, sometimes when this model is saying that it's going to be state or scenario number 3, actually it tends to also be in real life like a scenario number 5. So you can quantify that, or you can still try to extract some information in terms of what may happen for the next season or for a particular period in that season. So that's it. So I'm happy to answer a few questions. I'm sorry if that was too fast.
Great. Thank you, Angel. We had a very nice presentation, and we do have some time for Q&A. Chunzai, do you have any thoughts or questions before we go to the audience?
I have a question. In your slide 3, you show different kind of type of weather type, right? And then slide 4, you show the corresponding SST distribution for this different weather type. My question to you is, do you have any idea how this SST produces the weather type shown in slide 3?
Yeah.
I mean, can it?
Sorry. Yeah. Please go on.
So let me repeat my question. In your slide 3, you show many different type of weather type, right? And then in your slide 4, you show corresponding SST distribution associated with this weather type. My question to you is, do you have any idea how this SST normally produce the weather type?
Yeah, so we have an idea, and I don't think that I'm gonna go too deep into that one. I think that actually you will be able to see a lot of what's going on in terms of this mechanism, even how that relates not only with SST but also with, for example, easterly waves, like in a companion, poster by Nicolas Vigo, which I think is also like in the audience. But basically, I think actually in the last presentation we were seeing a few of these relations, like SST also modulate the occurrence of the Caribbean level jet, and there is also like interaction between the two basins, between the Pacific and the Atlantic, that changes the moisture fluxes and the moisture availability to produce this extreme event. So that is part of the work that we are doing actually in this paper, and I think that, you know, like later I will be able, once we have answer for all these questions, I will be able to provide a better explanation. But so far I want to focus on the aspects related to the methodology for the extreme scenarios, extreme rainfall scenarios.
Okay, thank you. Yeah.
Great, thanks, Chunzai. Let's take this other question before we break. We have a question from Eric Alfaro. He says, hi, Angel. Maybe I'm missing your point, but why did you do the study for boreal winter season and not for a season inside the rainy season, like the late boreal spring, early autumn in the region?
Yeah, sure. Hey, Eric, how are you? So the thing is that we, as I mentioned before, I can share with you like offline a few of these results. We did this for December, January, and February, and also for June, July, August. And obviously we can do that for other seasons if you're interested too in that one. I'm showing this one just to illustrate the method, but also because for DJF we will be able to capture part of the predictability that we'll be able to capture is related to ENSO. So obviously the predictability for June, July, August is a bit different actually. The SST patterns and the, let's say, climate drivers, the specific weight of the climate drivers is different, but there is no problem about, you know, applying the same methodology for the rainy season, or one of the rainy seasons.
Great, thank you. Okay, if you have any other questions, go ahead and type those into the chat feature and we'll queue those up and send those to Angel for him to answer afterwards. Thank you for participating today in Session 3. We're going to break for a little less than 1 hour, about 55 minutes. During this break, we're hosting our virtual poster session. So we do encourage you to go visit that. Today's poster presenters will be online for the next 55 minutes to kind of answer your questions in real time. When you go to the poster gallery, you click on a poster, you scroll to the bottom, and there's a commenting feature, and you can see previous comments and answers as well as add your own to that. We'll begin promptly again at 3:30 p.m. Eastern Daylight Time. You can leave your system on and connect it during this hour break if you like. We're going to leave everything up and running, and we'll see you back here at 3:30. Thanks, everyone.